Hi, this is going to be test prep for test number 10 in 3004 in 2018. We're going to look at the 2016 test number 10. First question is, cooling water available at 6 degrees is used to condense steam at 30 degrees in the condenser of a power plant at a rate of 1 kilogram per second by circulating the cooling water through a bank of 5 meter long, 1 centimeter internal diameter thin copper tubes. Water enters each tube at a mean velocity of 5 meters per second and leaves at a temperature of 24 degrees. Tubes are nearly isothermal at 30 degrees. So this is the surface of the tubes. And we're asked to figure out the rate of heat flow into the water per condenser tube, the LMTD of the exit relative to the inlet, well, also the surface in there too, right? So the LMTD of the exit to the surface relative to the inlet to the surface, that is. The average heat transfer coefficient between the water and the tubes, and the number of tubes needed to achieve the indicated heat transfer rate in the condenser. So this 1 kilogram per second here is not talking about the flow rate of water through the tubes. This is the condensation rate of the steam on the tube surfaces if you add up all the different tubes. Okay, so we are working with the stuff from the second half of chapter 19. And we have a constant surface temperature condition. So we're left with this, this information here, this setup. So we have our definition of the heat transfer coefficient, the convection coefficient, that is, for this kind of heat flow. The rate of heat flow is convection coefficient times the total surface area times, for a constant surface temperature condition rather than constant heat flux, the LMTD. And this is kind of like the definition of the convection coefficient for the constant surface temperature condition. So this is telling you how the total heat flow is related to the surface area and temperature difference through a convection coefficient. The temperature difference to use is the LMTD because it's not a constant temperature difference between the wall and the average of the fluid all the way along. So this is ultimately the energy that is ending up in the fluid, and so that would be the mass flow rate of the fluid times its heat capacity multiplied by the exit minus the inlet temperature. And if you need to figure out the exit temperature, then it's convenient to use this one in terms of the number of transfer units. So we're going to need that later for the second question, actually, but not for this one. So the first thing that we're going to look at in this setup is the total rate of heat flow into each tube. So we have a few different parameters for the water here. Let's just kind of write down what we've got here in our computer algebra system. So the inlet temperature is equal to 6 degrees. The surface temperature is equal to 30. The exit temperature is equal to 24. We know the water entering, the flow rate of the water is 5, and we know the length is 5 meters. The diameter is 0.01, so capital D is a reserved term in Maple for the derivative, so we can't use that. We have to use a different symbol for that. Okay, so then we can figure out the cross-sectional area, and that's going to be pi, let's do 3.14159 times the diameter squared over 4. So there's our cross-sectional area. And what we can do with that is say that the volumetric flow rate would be the velocity times the cross-sectional area. And so the mass flow rate would be equal to the density times the volumetric flow rate. So we're going to need to figure out a density. Before we know which density to use, though, we're going to need to look up what the parameters of the, we're going to need to figure out which temperature to use for that. So the temperature we're going to use is the bulk mean fluid temperature. This would be the exit minus the inlet temperature all over 2. So that's just like the average of the average fluid temperature, not the wall temperature in there. Like imagine if you had a very short pipe, then the wall, yes, is at 30, but the fluid might enter at 6 and leave at like 6.1. So it would be, and if these are the average temperatures of the fluid, it makes more sense to use something closer to 6 for that. So that's why this doesn't account for, this doesn't use the surface temperature there. Okay, so yeah, we've got a bulk mean fluid temperature of 9, so we'd want to look up the water properties around 10. Wait a minute, 10 seems way too close to the inlet temperature rather than the exit temperature. Aha, okay, this isn't the average, this is a difference. So the bulk mean would be the average of the inlet and the exit temperature, so we want to add those and divide by 2. Yes, of course. Okay, so 15 degrees is our bulk mean fluid temperature. So for the properties of the fluid, we are going to go over to the appendix in the textbook. So appendix 15, we're dealing with water, and then at a temperature of 15 degrees, the first property we need is the density 999.1. So we'll grab that one. Rho is equal to, maybe we'll put that up here. Rho is equal to 999.1. And there we go. Okay, so we've got our mass flow rate. We're probably going to need some other properties of the water, but let's hold off on those for now. Okay, so we also have the ability to figure out what the heat capacity is. I guess we'll need that right away in order to calculate what's going on with this Q dot stuff and this M dot Cp. We've got the Te minus Ti, so we just need Cp, and then we can figure out Q dot, which would be the rate of heat flow into the water per condenser tube. Okay, so yeah, Q dot would be equal to M dot Cp times Te minus Ti, and all we need now is the heat capacity. So back over to the appendix, and the heat capacity at 15 degrees is over here. So specific heat, 4185 joules per kilogram Kelvin. Okay, so Cp is 4185, and that tells us that the rate of heat flow is about 30,000 watts. So the next thing is to figure out the LMTD, and we can work that out just from the temperature differences. LMTD would be equal to the Ti minus Te over the ln of Ts minus Te over Ts minus Ti. Okay, so this should be, after we maybe put in an evalf there to turn it into a floating point evaluation, this should give us something that's kind of like the average temperature difference between the wall and the fluid. So we start off at 30 degree wall to 6 degree fluid, which would be a difference of 24, and then we end off at 30 degree wall to 24 degree fluid, which by symmetry I guess would be a difference of 6. So the average difference of 6 and 24 would be 15. But the LMTD accounts for the fact that actually a lot of cooling happens right at the beginning when we have this big temperature, or a lot of heating in this case happens right at the beginning where we have this big temperature difference. So it doesn't spend much time at the 24 degree temperature difference compared to how much time it spends closer to the 6 degree temperature difference. So that's why it weights it a little bit lower than just a raw average would. So that's our LMTD. Okay, so third part, average heat transfer coefficient between the water and the tubes. And we've got Q dot is HAS delta T ln, and we figured out Q dot. So then if we can figure out the surface area, which is pi diameter times L, so pi d is the circumference, and then multiply by the length of the tube, there's our total surface area. And what we'll do is take the surface area and the delta T ln and Q dot, and then solve that equation for H. So H would be equal to Q dot over AS times LMTD. And that tells us that the heat transfer coefficient is about 14,500. Final thing we need is the total number of tubes to get that heat transfer rate in the condenser. For this, we're going to need to look up a different fluid property for the water. So specifically, we're going to need to figure out how much energy we get by condensing water at water vapor into liquid water at 30 degrees. So that also is in the is in this convenient appendix here in the textbook. What a textbook. We've got an enthalpy of vaporization here of 2431 kilojoules per kilogram. Okay, so in joules, the HFG would be equal to 2431 E3, and the question tells us that we are condensing at a rate of 1 kilogram per second. So then we need Q dot total would be equal to, so this is like over all the different pipes. If it's coming from the condensation, then we've got HFG. So that's the that's the energy that's released per kilogram, and then we're multiplying by 1 kilogram per second. So that's what's going to give us the watts there. So this is the rate of energy transfer from the steam into the pipes. And then to figure out the number of pipes, if this is the total energy transfer, and then Q dot is the energy transfer per pipe, then we can get pipes if we take Q dot total and divide by the Q dot per pipe. The pipes will end up in the numerator there. Okay, so number of pipes is about 83. One last point is in this setup, you may have noticed that we've got our convection coefficient just determined directly from this, but in the things later on in chapter 19, we learned information about how you could actually calculate the convection coefficient if you know the fluid properties. So let's have a look at this different way to calculate the convection coefficient and see how it compares. So the separate way to calculate convection coefficient would be first to figure out the Reynolds number, which would be the density times velocity times diameter over the viscosity. And then once we've got the Reynolds number, we're going to figure out the friction factor through maybe the Haaland equation. F would be equal to 1.8 times log 10, log 10 of 6.9 over Reynolds number plus epsilon over diameter over 3.7, all to the power of 1.11. Let me put in an extra bracket there. Maybe. Let's see. That would be that. And this would be, yeah, okay. And then we take that thing to the power of -2. Okay, so there's your friction factor. And then once you have that, so this is because this is only if it's turbulent with the Reynolds number, but we really need to check that. I've done this one before, so I think I'm just remembering that it's turbulent here when I put this in. If it wasn't turbulent, you'd use a different formula for Nusselt number, which doesn't need the friction factor. But because it is turbulent, we're going to try using maybe this one to see if that is giving us the right result here. So we figure this out. We'd use this Nolinsky equation to figure out the Nusselt number, and then that will tell us what the convection coefficient is. So we'll figure out Nusselt number from Nolinsky equation, F over 8 times Reynolds number minus 1,000 times the Prandtl number divided by 1 plus 12.7 times F over 8 to the power of 0.5 times the Prandtl number to the power of 2 over 3 minus 1. So that's going to be our Nusselt number, and then we're going to figure out that the H is equal to Nusselt number times the K divided by the diameter. So Nusselt number is equal to H times diameter divided by K. So then in solving that for H, we'd figure out our new formula for the convection coefficient. If we were to use the fluid properties to figure out what the Reynolds number is, and then use that to figure out what the friction factor is, and then use that to figure out what the Nusselt number should be, and then use that to figure out what the convection coefficient should be. But a lot of this is based on experimental fits and things that we didn't really know and had to look up and guess, like the roughness. So in addition to that, this Nusselt number formula is really for smooth pipes, so we can't, we don't expect it to be super accurate for the roughness number. So that means we would probably get a result that's not as accurate as the one that we got before. So more on that after we finish this calculation. looks nuts because we need more parameters subbed in. So specifically, it looks like we need the dynamic viscosity, and we're going to need the surface roughness and the Prandtl number, and then at the end there, we're going to need. Did we look up the conductivity? Oh, there it is. We're going to need the conductivity. Okay, so we need those 4 parameters. Let's go and get them. So back to the table here. At the 15 degrees, the dynamic viscosity is 1.138 E minus 3. The Prandtl number is 8.09. The conductivity is 0.589. And the last parameter that we don't have yet is the roughness of the copper. And for that, we're going to look at a different spot in the textbook. So this is when we first were talking about convection, and we were doing, let's see here. We did some surface roughness stuff, and where's that? Oh, wait. Not when we were doing convection. When we were doing the internal flow in pipes, the turbulent flow section was the first time we needed this roughness calculation. And so for copper tubing, the roughness is probably around 1.5 microns. So let's put that in. 1.5 microns. Okay, so now we should have everything calculated. Yeah. All right, and what have we figured out? So we figured out from the actual heat transfer that occurred in this setup. So from knowing the inlet and the exit temperature, and knowing the surface area, and knowing the actual heat flow rate because of that temperature difference, we can figure out what the convection coefficient must be so that this is actually true. And from that setup, we determined that the convection coefficient is exactly 14.491. And then we said, all right, well, for this set of fluid properties, we know what the Reynolds number should be. And then we can figure out what the friction factor probably is, although that was based on an estimate of surface roughness and experimental fits. And then we can figure out what the Nusselt number, again, probably should be, which determines the convection coefficient. So this is a lot less exact than just being able to go from kind of the definition of the convection coefficient to figure out what it is. So if you have enough information, if you have the inlet and the exit temperature, then you're pretty much good to go, and you can just use this equation. If you don't have one of those, you're missing maybe the exit temperature, then this whole method falls apart, and you have to go through figuring out the convection coefficient to go through solving the whole thing. And that's what we're going to do in the next question here. Air at 20 degrees C enters a 1 centimeter diameter, 15 centimeter long circular tube at an average velocity of 3 meters a second. The tube wall is maintained at a constant surface temperature of 160 degrees C. Using the properties of air at 50, and noting that the dynamic viscosity of air at 50 is pretty different than at 160, figure out the Reynolds number, hydrodynamic and thermal entrance length, Nusselt number, and convective heat transfer coefficient. Okay. So this time, the equations that we've got, constant surface temperature. So again, we're going to use the LMTD rather than just a fixed temperature difference to figure out what's going on with the heat transfer. This time, we've got a missing exit temperature. So we know what the inlet temperature is, but we don't know the exit temperature. So what can we do? We can say that Ti is equal to 20. We can say Ts is equal to 160, constant surface temperature again. And we can put in some fluid properties. So rho is 1.092. This is also in the textbook table, I want to say A21 or A22 for air. CP is 1007. K is 0.02735. Nu, the kinematic viscosity, is 1.798 E minus 5, and the Prandtl number is 0.7228. Okay, so then we've also got mu is 1.963 E minus 5, and mu 160 is equal to 2.42 E minus 5. Okay, so then we can figure out the Reynolds number. I guess we also need to put in the dimensions. So L is 0.15, diam is again 0.01, and the velocity is 3. So Reynolds number is the velocity times diameter over the kinematic viscosity. All right. Next, hydrodynamic and thermal entrance lengths. Now that we've got the Reynolds number, we can say, hey, we are in laminar flow. So for the entrance length, we're going to go to the first part of chapter 19 here, when we were talking about, oh, wait a minute. Flow in tubes is the first part of the second half of chapter 19. So that's 19.5 there. And we have these nice formulas for the entrance length in laminar and in turbulent flow. Because we're in laminar, then we can say the entrance length for the momentum part is about 0.05 times the Reynolds number times the diameter. So LH is 0.05 times Reynolds number times diameter, and the thermal entrance length, LT, is LH times the Prandtl number. So in turbulence, these things coincide, but in laminar flow, they can be different. So we've got our thermal entrance length is 0.603, which is a lot more, 60 centimeters, than the length of the tube, which was only 15 centimeters. Now, what that means is that we are going to need to use a special formula for the Nusselt number. So in order to figure out the Nusselt number, we go down into the 19.7 notes. And for fully developed flow in laminar, it's just 4.36 for uniform surface heat flux, or 3.66 in this case for uniform surface temperature. But we actually, it's certainly not fair to say that this entrance length of 60 centimeters is negligible compared to the total length of the tube, when the total length is actually shorter than that. So we definitely are still in developing flow here and have to use one of these different formulas. So for a circular tube, we have two different formulas that the book gives us. We've got this constant viscosity formula, and we've got this viscosity variance with temperature accounting formula. So this one takes into account the fact that viscosity changes with temperature. So since the question gives us this pretty big hint that the viscosity is pretty different with temperature for at the surface compared to the bulk in this setup, we better use this formula. So the Nusselt number would be equal to 1.86 times Reynolds number, Prandtl number, diameter over length to the power of 1/3 times mu 160, mu 50 is the bulk mean fluid one, and then we've got mu over mu 160, that's the surface one, and we're going to take that to the power of 0.14, so that should be our Nusselt number. Okay, 7.796, and notice that that is actually a lot higher than we would have gotten for the fully developed one, 3.66, and that makes sense. You'd expect the Nusselt number to be higher if we're still in developing flow, because we have shorter distances from the higher temperature in the sort of free stream region near the center compared to the walls. So sharper gradients at the walls, more convection. Okay. Next, it asks us to figure out the convective heat transfer coefficient. So the convective heat transfer coefficient is from the Nusselt number. H would be the Nusselt number times K over the diameter. And we've got 21.3. Okay, Now the question doesn't ask us to do this, but we could go on from there and figure out the exit temperature by figuring out the number of transfer units. So the number of transfer units would be the exponent in this thing. It's H times AS over M dot times CP. So there's a lot of things the question doesn't actually ask us to figure out here. So AS, the surface area, would be pi times diameter times L. AC, the cross-sectional area, is pi times diameter squared over 4. And M dot would be equal to the velocity times the cross-sectional area, that's the volumetric flow rate, times the density. So we should be good now to figure out the NTU. Yeah, so the NTU is 0.3878. So we haven't had much distance to transfer heat yet. So we expect that we're not going to be that close to the wall temperature by the time we pass this. So according to that second part there, this is how you can figure out the exit temperature. Remember that the whole reason you have to use this this Nusselt number method to figure out the convection coefficient is because we're missing that exit temperature. Now once you've done that and you've got that convection coefficient and the entrance flow stuff and the surface temperature, the way to find that exit temperature is through this formula. So that's what we're doing now. So TE would be TS minus Ti times e to the negative number of transfer units. And we've got 65. So 65 is the exit temperature, and we can check whether or not we used a very good temperature to figure out the fluid properties. So the actual bulk temperature would be TE plus Ti over 2, and that is 43. So we used 50 degrees, not so bad. If you didn't know anything about what the temperature should be, then this would be kind of like an iterative step. You would go through the whole thing you'd kind of just guess what the exit temperature would be, use that to figure out your fluid properties, calculate everything out, see what the exit temperature actually is, and then use that to figure out the bulk mean fluid temperature and do the whole thing again. Okay, hope that helped. Thanks for watching. Have a great day.